All right. Hello, everyone. This is video 10 in my series of trying to learn the NIM programming language using Gemini 2.5 Flash from Google with a custom gem while doing problems off of Project Euler. Today we're doing problem 10 to actually do the learning. So, um, something I want to say about problem 10 is it's a problem that will challenge you not in the solution, but the implementation of the solution. So I will say that right off the bat. So let me show you what I mean. So this is a very simple question. For example, the sum of the primes below 10 is 2 plus 3 plus 5 plus 7 equals 17. Find the sum of all primes below 2 million. Not at all difficult. What you would be doing is really just have an iterator and iterator. After that, you will have a function that takes the number from the iterator, checks if the number is a prime, if prime. I typed and then I scribbled. I'm doing both, but really, and step 4 is to just, if it's a prime, add it to a final sum. Fairly simple. For example, you can do, let's declare let me activate my highlighting first. Final sum, call it an int. Now you will do for I in 2 less than 2 million, if is prime, final sum equals to I, echo, final sum, define the is prime function. So define the is prime function like this, and just it for I in 2 less than number, if number mod 2 equals to 0, return false, return true. This looks fine. Now, the issue here is I ran this, and this ran in 515 seconds, really. So about 6 minutes and 35 seconds. And the issue here is, in the past I've done, and the answer I got was this. Oops, sorry, that's not what I was trying to copy paste. What I was trying to copy paste is this, and that's the answer we got. And if you sign in, CAPTCHA is this, and summation of primes. And the answer is this. The correct answer is this, and this is the answer we get. Right, so this is good. This is good. This is good. This is the correct answer. But I think this is more of a uh, you can do better face than a smiley face. And I think the issue is that in the past I've used a first principle approach to implementing the is prime function by just brute forcing all the numbers. And what has ended up being the case is that for any number n, if it's small, it's fine. But if it's a huge number, if it's like the biggest prime number less than 2 million, if that is n, then it needs to go through all the numbers from 1 to from 2 up to n to that number. And for the second largest prime number, it's the same story. So what really ends up happening is I think we end up with a massive big O notation where um, for for the task at hand, if you have all numbers less than 2 million, you are doing, I think, big O notation of n times n factorial, maybe, or maybe just n factorial. Might just be n factorial, one or the other. But this is just a massive big O notation that just doesn't scale and ends up taking um, almost 7 minutes for the problem. So I think we need to challenge ourselves in the implementation of the is prime function. So one of the simplest things we can do is if you think about it, for any number n, if you divide it by n by 2, you'll end up with 2. But for any a greater than 0, really, or greater than 1, for convenience sake, we can say greater than 1, you'll end up with something less than 2, more than 1, right? For example, for 100 divided by 50, you get 2, but add anything, um, sorry, greater than 0. Greater than 0 is correct. Greater than 0, for example, 1, you will end up with something between 1 and 2. So we really, for any number n, we don't need to go past n by 2. So that eliminates so many tasks, so many things that the program needs to handle. But then again, there's also the thing that we don't need to also, we also don't need to do something like n minus 1 by 2 because it also, for example, 100 divided by 49 is almost guaranteed for example, something like an n divided by n minus 1 by 2 is also guaranteed to be something between 2 and 3, a decimal between 2 and 3. So looking around, I found out that it's much more generalizable. There's something much more generalizable. We can't go around implementing these weird rules one at a time. So looking around, what I found out that a number is prime. A number is prime. Any number n is prime if it doesn't have a factor between 2 and the square root of n. And turns out the idea is you prove this by contradiction. Mathematical logic, using mathematical logic and logic of contradiction, you prove this as for any number n, suppose that it's a composite, which means suppose it is a composite. Say it has no factors between 2 and square root of n, and because it is composite, it must be possible to express n as a times b equals to n. And the relationship between a and b can only ever be a is less than or equals to b. For example, if you think of something like number 36, 2 and 18. 2 and 18, 2 is less than 18. Or 3 and 12. Or 4 and 9. Or 6 is equals to 6. In all of these cases, 1, 2, 3, 4, A is less than or equals to B holds. Well, what about 18 and 2, right? 18 and 2. You just swap labels, right? You will always put the smaller number here. You'll always put the smaller number here. It's not about the symbols. It's not about the numbers as much as the relationship between the numbers and the symbols and how you position them. So for a composite number, for any composite number, say we are saying that there's no factors between 2 and square root of n, and then we are saying that a times b equals to n. That has to be true. That has to be true. This is something we suppose, and this also has to be true, right? So two things are possible. Two things are possible. There are two possibilities with respect to square root of n. The first possibility is a is less than square root of n, but then that violates this supposition, right? This directly violates this supposition. The second possibility is a is greater than square root of n, but because if a is greater than square root of n and a is less than b, that brings us to square root of n, a is greater than square root of n, and b is greater than square root of b is greater than a, which is also greater than square root of n, which means this translates to something greater than square root of n times something else greater than square root of n equals to n, which is self-evidently cannot be true. So for a number n and its square root n, for it to have no factors between 2 and square root of n, it cannot be composite, it can only be prime. So it turns out that is how you solve the big O notation of prime numbers. I'm sure if with even bigger prime numbers there's a better solution, but for now, to me, that is the most accessible solution that completely eliminates the vast majority of the task that the repetitive task that the program will have to do. The one I came up with and I was pondering about was just something like n divided by n by 2 plus a for any a greater than 0. We don't need to do that, but turns out if you have no factors between 2 and square root of n, then n is a prime number. So, and the way to implement that would be to just change the is prime function ever so slightly. We will implement a square root. We'll implement a square root. Because square roots produce floats, we will use something similar to C's ceiling to go from something like, for a square root of 10, we would go from something like 3.33 to we want to go to 4. And I think that's what we'll do. So in the nim programming language, how do I'm so sorry about the browser, get the square root of a number. Okay, sqrt from the math module. Okay, so I think what that is saying is just this. Import math, that's how you import a library. And you will do sqrt type mismatch expression sqrt number int expected 1 first mismatch at position type mismatch number int. What? So to me that is all right. So let me make it a bit easier to read the problem. Okay. That can't be right. Oh, did I not save it? Oh, oh, sorry. Oh, all right. So I think I know the issue. Okay, so this was what I was trying to do. All right, so error type mismatch, expression square root, number, number int expected one of first mismatch at position I. Okay, so for position I, it's expected either a float 32 or a float 64. Does the sqrt function expect a float? Does it? It will return a float, actually. So that's the oh, this will return a float too. So that's right. Okay, so and okay, so syntax, please provide the syntax to show me how, oh, show me how to convert an int to type float in nim. Float my int. Okay. And so okay guys, so because square root needs floats, square root needs floats, and square root can return floats, we need to do a couple of type conversions. So we would be doing so we would be doing float 64. Yep, and expression has no type or is ambiguous. Right, so because a range needs integers, and because square root can return floats, because square root most likely returns floats, we need to now do a double conversion in this way. And the +1 is for the sake of the ceiling. So I'm sure there's a ceiling function, but I just want to do it this way. So I think, okay, so I think this is it. All right, so ever so slightly, we extend the function nim. And let me check. Okay, so 1, 2, 3, 4, 5, 6. That's not right. There should be one more zero there. Okay, and let me read through this one more time. For I in 2 less than the integer or the square root of the float of the number +1, if number mod, oh, that should be mod I. I'm sorry if that's what I've been showing you for a little bit now. That should be mod I. Okay, so um, okay, so time now that we have done, probably should have changed the name, but once we have re-implemented the isPrime function, the time is 1 second compared to 515 seconds, so we are 515 times faster. And the answer is, let's make sure our answer is right. Let's go with a orange number. So the answer is correct. So the answer is correct. 14291382892. Okay, so I think that deserves a big old smiley face because we went all the way from here to here. Okay, so here we learned how to move past our old implementation and how to extend our old functions ever so slightly for a massive improvement in speed. We learned about a little bit about the math module. We learned about square roots, and we learned about type conversions and reading compiler errors. Cool. So, yeah, so problem 10. Looks simple, but can teach you a lot. All right, so fantastic. And let's look at problem 10. All right, I haven't done problem 10. In the 20 by 20 grid below, 4 numbers along a diagonal line have been marked in red. Cool. The product of these numbers is 26, 63, 78 times 14 equals to 1,788,696. What is the greatest product of 4 adjacent numbers in the same direction, up, down, left, right, or diagonally in the 20 by 20 grid? Okay, interesting. Things are getting much more, significantly more interesting, even though they have been they have been knowledgeable, but not that interesting. But now this looks interesting. All right, I'll see you in video 11.